Now let's talk about some counting word problems. Most counting questions don't explicitly involve sets like on the previous 2 pages. Instead, you're given some scenario involving either objects or objects that satisfy some rule, or collections or arrangements of objects, or just some situations that involve objects. You're given this in sentence form, and you have to figure out a way to count them. Here are some examples of counting questions. How many binary numbers are there with 9 digits? How many of those have 3 ones? In how many ways can you arrange 5 people in a line? How many ways are there to order a dozen bagels if the choices are plain, poppy, sesame, and everything? You can see this first question is asking us to count objects. The second question has some restriction related to those objects. The next question asks us to talk about arrangements of objects. The last question is asking us about a situation involving objects. And each one of these questions involves counting something. And even though they don't look like they involve sets, you are being asked to count a collection of discrete objects, which is our definition of a set. So let's develop some techniques for counting this type of question. One natural situation is that you're counting something that partitions into smaller, disjoint groups of objects. In that case, the strategy is going to be to count the smaller groups individually and then add them together. Here's a basic example. You have 9 short-sleeve shirts and 6 long-sleeve shirts. In how many ways can you choose one shirt to wear? There's 9 short-sleeve shirts, there's 6 long-sleeve shirts. You add them together, you get 15. Notice that we can understand this question as a question involving sets. We've got the set of all shirts that we're trying to count, and those are partitioned into the set of short-sleeve shirts and the set of long-sleeve shirts. Those 2 sets have no overlap. A shirt cannot be a short-sleeve shirt and a long-sleeve shirt at the same time. This is called the addition principle. If A and B are disjoint sets, then the cardinality of the union of those 2 sets is equal to the cardinality of the first set plus the cardinality of the second set. Let's say you have a whole bunch of sets that are pairwise disjoint. Then the size of the union is equal to the sum of the sizes of the individual sets. So let's say you're in a situation where it makes sense to apply the addition principle. You have some question that involves counting a collection of objects. You should follow the following steps. Step 1, identify smaller groups of objects that are individually easier to count. There may be some natural grouping of the objects, or you may condition on a particular property or numerical statistic that the objects have. After you've identified the smaller sets, verify that they're disjoint sets. One way we know that sets are disjoint is when we condition. If you condition on a particular property, then the sets are necessarily disjoint. Then count each smaller set individually and add the results together. Let's do a few examples. How many palindromes are there between 1 and 100? Remember, palindromes are words or numbers that can be written the same forwards or backwards, like ABBA or 35753. In this question, because we're only looking for numbers between 1 and 100, it probably makes sense to condition on the number of digits in the number. There are some numbers that are palindromes that are 1 digit long, and there are some numbers that are 2 digits long. Every number between 1 and 9 is a palindrome. It looks the same forwards and backwards, so there are 9 one-digit palindromes. On the other hand, when you have 2 digits, the number has to have the same digit in the tens and the units digit. We can see that these are indexed by what digit is repeating, and again, there are 9 two-digit palindromes. As you remember, we conditioned on the number of digits in the number, and so these are disjoint sets. Because they're disjoint sets, we can apply the addition principle, and we can see that there are 18 palindromes between 1 and 100. Let's do one more example where we show what can go wrong. In this example, there are 10 students in this class who speak Spanish, and there are 8 students in this class who speak Chinese. We might want to know how many students in this class speak Spanish or Chinese. If we tried to look at this as a question about sets, we'd have some large set of all students, and there would be a set of students who speak Spanish, and there'd be a set of students who speak Chinese. That's a natural way to try to break down this set. But what's the problem here? These two sets are not exclusive. They may not be disjoint. There may be students who speak both Spanish and Chinese. Because we don't have that information, and because these sets overlap, we cannot apply the addition principle. We're going to need another technique. I'm going to suggest that you go grab some pie and come back later. Okay, that's it for this video. See you shortly.